Okay, let's get started. Welcome to today's edition of the virtual seminar on precision physics and fundamental symmetries. Today's speaker is Jonathan Hone from ETH Zurich. Jonathan did his PhD in Oxford with David Lucas and Andy Steen. He then moved on to the ion storage group at NIST in Boulder with Dave Wineland and Dietrich Leibfried, where he's been involved in experiments implementing different aspects of scalability of the ion-trap quantum computer with beryllium and magnesium ions. And in 2010, he moved on to ETH in Zurich to start his own group, where he still is, as you can see. And he's been, his work's been recognized widely in the community. Some of the evidence we can see on the title slide already. And he's going to be giving us a presentation on scaling quantum computing with trapped ions today.
Okay, thanks, Christian. Also for organizing this seminar series and reacting so quickly to you and the other co-organizers. It's a great pleasure to be here and to be able to introduce some of our work, which I've titled this talk Scaling Quantum Computing with Trapped Ions. But as you will probably see, there's limited scaling here, but there's more thinking about and experimental investigations of methods which might be useful in trying to scale up quantum computing with trapped ions. And in particular, here's just a view of that from the sort of conceptual angle, if you like. Here's actually a chip. This chip here is got gold electrodes on it. And above this chip, about 50 microns above this chip, we can trap individual ions. But the sort of new feature of that chip is not so much the ion trapping itself, though that's something which these surface traps are sort of 15 years old or so. And here you see the electrical wiring. There's a bunch of wire bonds that you can see attaching to the chip here. But on the right-hand side, this slightly more messy structure is actually a bundle of optical fibers, so 8 optical fibers, which go into a V-groove array, and they're then coupled into this chip in order to deliver light to the ions. And so that's a relatively new approach, and I'll tell you some results that we've had recently from that approach. And that's sort of one key, if you like, to thinking about how to make more complicated control, because by these methods, and you already see it here, we can deliver many channels of light to a set of ions. And that's a very challenging thing to do if you work in a laboratory with free space mirrors. So that's the experimental aspect of the talk today. I'll also, in the second half of the talk, cover some theoretical work, which is now hopefully turning into experimental work on thinking about sort of fundamental technological challenges in scaling up. So before I proceed, let me just thank all of our funders, a variety of those, and then I move on into the talk. So the talk is primarily aimed at quantum computing, and I thought it worth just motivating and saying what's required in thinking long-term about quantum computing. So quantum computing is really motivated by graphs like this. This is a bit of a sort of public talk type image, but you should imagine a linear scaling, if you like, in the size of a problem that we have. Sorry, my computer just did something funny. That we have along the bottom axis. And up the left-hand side on the vertical axis, we have an exponential scaling, which is something to do with runtime. And what you really see is that the prediction coming from 1995 or so for certain problems is that there are sets of problems, and I think the most interesting ones of those are in physics, where the scaling on a classical computer is exponential in somehow the number of bits or so you might use to specify your problem. Meanwhile, in quantum physics, using the sort of base rules of quantum physics, superposition and entanglement, it should be possible to make a computer where the scaling is fundamentally different. Yeah? And at some level, what that means is if some function's going up exponentially and some sub-exponentially, the quantum computer should be able to finish problems in, say, a reasonable time of a year. That's a very long time to wait for your problem to finish, but it's much shorter than waiting for the age of the universe, which is what the classical computer would require. that creates quite a big challenge because actually classical computers are superb. They're probably the most advanced devices we have on the world today, and they can do extremely impressive things. Yeah? So in order to make quantum computers useful, it is likely that we have to go to pretty large scale devices on their own. So let's just look at a type of problem that might be interesting to solve on such a device. So the molecule you see here is FOMO-Co, and it's actually a complex that's found it's used by plants, or it's somewhere in the pathway of the catalysis path in plants. And what we know about plants is that they're extremely efficient at extracting energy or converting substances and producing ammonia and other nitrates, which are useful for generating their energy sources. Right? And by contrast, if you like, if you look at the way we do these sort of things in the Haber process, you'd find it's an incredibly energy-intensive process. So actually, there's a decent chunk of the world's energy goes into running the Haber process. So finding out structures of molecules such as this, that's an important problem, even in practical terms for our society, because it'll save on resources. And of course, that's a key concern in the years ahead. But what you see down at the bottom here is a result from my former colleague, Matthias Treuer, and he asked the question, you know, how many qubits would you need for doing this, and how many operations would you need to do? And you see that the numbers are large, right? So there's about 1 million qubits, and if you're using individual trapped ions to store information, that's meaning you've got to control systems of 1 million ions or so, and you've got to control them well enough that performing 10 to the 17 operations on them keeps your system quantum enough that you're able to get good results out of this. And the caveat to that is actually that most of what a quantum computer will do once it's at this scale, as it'll just be correcting its own errors. Even if you make a very good job of building such a device, it spends almost its entire time correcting errors and almost none of the time actually computing. So let me just, for that, you need to know a little bit about how we correct errors, and I'm going to give you the sort of simple introduction. So here what you see is a sort of cartoon. This is actually a cartoon from Helmut Rich, and it's sort of advertising for an earlier paper of Rainer Blatt's group, actually. So what you should think of here is that each of these individual nodes, if you like, we place a two-level system, a qubit, and that for us would be, in our lab, a single trapped ion. And each of these qubits, if we want to store information in them, we choose, for the purposes of correcting errors, not to store information in individual qubits, but rather to store information in a Hilbert space, which is formed by, say, 7 individual qubits. So these will be the 7 that you see here. And the advantage of that is that noise generally acts, or we can make the assumption, and it's quite, you can devise your architecture to realize this, that noise primarily acts locally. So if you have information that's stored in correlations across lots of different places, then the noise acting locally has a smaller impact on the information than if you'd stored all of your information locally. Yeah? And then the other trick to quantum error correction is that you would like to know if an error happened. So if you have just a single bit and you want to know, did it flip, then you would usually go in and measure that bit. And you probably know from your quantum mechanics, if you measure quantum mechanical systems, you have a very strong impact on that quantum mechanical system. So you definitely don't want to go in and measure information in quantum mechanical systems, but quantum error correction gets around that by measuring correlations, okay? So instead of saying, is this specific bit 1, is this one 0, is this one 1, you ask the question, are all of these quantum bits the same value? So they may be all at 1, they may be all at 0, or in fact, the more usual thing is to say, are an even number of those at 1 or an odd number of those at 1, yeah? And so these sort of correlation measurements are what form error checks. If an error happened here, then the correlation between all of these will have changed, and that's the key to being able to diagnose and correct errors, okay? So the 7 qubits, or these 7 blobs that you see on this small lattice here, that's sort of the smallest error correction code that you can think of doing. and it's still just about out of range for the experiments of today. Yeah. Nevertheless, the landscape in the background is more like what you might think a quantum computer has to be. Okay, so even a single qubit in a quantum computer, you can make an estimate for how many ions or how many individual physical systems are required per logical qubit. So that's I store information in a logical qubit, but in order to do that in an effective error correction code, I need large numbers of individual qubits per logical qubit. So if my error rate is around, is low, right? So this is saying the probability of me getting my gates wrong is 5 times 10 to the minus 4, right? 5 parts in 10,000. I probably need still thousands of ions per logical qubit to do a serious algorithm, such as the chemistry that I showed you earlier. In fact, these numbers are sort of made for a Shor's algorithm, yeah? Which is a factoring type algorithm. And even if the errors get a factor of 10 better, you still see it's very large numbers of ions, even per a single logical qubit. Yeah? So what this says is that a quantum computer is a really challenging device. Of course, we hope that theoretically people come up with better codes or codes that use lower numbers of qubits, but at the moment we don't see those. And so what we see is experimentally we have to scale up dramatically. Yeah. So that brings us to trapped ions, and I've sort of heuristically referred to trapped ions as quantum bits. Trapped ions, as you will be aware from these seminar series, are excellent atomic clocks. Each one of them you can find, or in many of them you can find internal states which have very long lifetimes, and where you can control superpositions of states, and they process at an extremely predictable rate, and that's basically an atomic clock, and it's the same thing we need for a qubit. Yeah. So the additional thing we need for qubits is that these ions can interact, and that we can form networks where we can do conditional operations between, for instance, the ion sitting here and an ion sitting over here. Or indeed, if you think about the setup I've drawn here, these would be the idea that a laser is directed at 2 ions in a long chain here, and you might want an interaction between this ion here and this ion here. Yeah? And the reason that you can think about having those interactions is that the Coulomb interaction means that all these ions repel each other. So if this ion moves, then this ion will also move, because the Coulomb interaction creates a force that drives the chain, and that will move the other ion. So already the motion of these ions, because this is a rigid structure or a semi-rigid structure, is got some correlations in it, if you like. And so the question is, can you couple the internal states of the ions, these excellent atomic clocks, which of course is extremely well isolated from the outside world, can you couple them to that correlated motion? And so that's really a key to generating correlations, or what we call entanglement in quantum physics. And the way that we generally do that, though of course any of you who attended Christian's lecture would have seen this was done with microwave fields, but the way many experiments do that is with optical forces from lasers. And actually the microwave gradients that Christian might have told you about, you may have heard that talk, has the basic same principle. You want a force, and the force should be near resonant with the vibrational frequencies, so the frequencies at which this entire chain likes to oscillate. But in addition to that, then the direction of the force on any given ion should depend on the internal state. So the clock can be in 2 spin states. I can think of an atomic clock as being spin up and spin down, or superpositions of those. And now we imagine that the force direction just depends on which of those 2 states you're in. So on top of that, and I just draw a 2-ion system, you should imagine that the 2-ion system is springy, and that's because there's a Coulomb interaction between the 2. Okay, so let's just examine if I have 2 ions, and they're both in the same state. So let's say they're both in the state 1. Then if they're in the state 1, they'll feel a force to the right-hand side, if you like. So what does that mean? That means that if they're both in the state 1, then they get the same force, yeah? And that's not going to excite the spring motion, because the spring gets excited by out-of-phase motion of the ions, okay? And the same is going to be true if these ions are in the same state, but they're in the 0 state. they'll also get excited. They'll try and drive the same force, but they won't excite the spring type motion. But if they're in different states, then the forces on these two ions will be in opposite directions because each state has an opposite direction of force. And so either if they're 1 or 0, or if they're 0 or 1, you will excite this springy motion. And if you're near to resonant with that motion, you'll get oscillations and you'll get excitation. And what we do is we arrange the optical fields such that after a certain period, that excitation has gone away again. But what happens in quantum mechanics if you do that is that you pick up a quantum mechanical phase. So you see that if I excite the spring, then I can pick up this factor of I sitting in front of the state. And if I don't excite the spring, then I don't pick up any phase at all. Yeah. And what this sort of operation does when you pick up just phases on these 0, 1 and 1, 0 components, that's actually a useful 2-qubit gate. If you apply that to a pair of ions in the right sort of state, you generate maximally entangled states, and those are sort of characteristic of what's useful in quantum computing. Yeah. Okay, so that's sort of the basic layout. And as you see from this picture taken from Rainer Blatt's group, then people are able to do these sort of operations now on really large numbers of ions. So you see basic control, and I say that there's a slight qualification there, which goes up in systems of 50, maybe 200 ions, say in John Bollinger's penning trap, where you see systems where such couplings with these sort of phases are being generated between many of the ions in those systems. For quantum computing, it's a little bit more challenging. You have to have, in general, extremely good control and an extremely good individual control of every single atom. And that means systems more like 10 qubits are sort of state of the art, or 10 ion systems are state of the art today. Okay, so how do we trap these ions, and what's the sort of progression as we think about scaling these systems up? So this is a trap from the Innsbruck group. This has been in Rainer Blatt's group actually since the 1990s, but I think is still one of their most successful experiments, which just says that the good designs last, if you like. Yeah. So what is it? There are 4 blades, actually. You see 3 of them. These are metal blades. And on 2 of those are applied an RF potential, okay? On the end caps, which you see as these little pins sticking in from the end, then there's a static potential applied. And a static potential can confine in 2 dimensions, but will anti-confine in the other dimension. So in these traps, the RF potential, which is basically a kinetic energy as a function of position, which you make sure the kinetic energy of a driving electric field is 0 at the trap center. This is the thing that allows you to perform 3-dimensional confinement. And so these are the traps, as I say, doing very successful quantum information experiments. But if we think about scaling to more than 50 ions or large numbers of ions, then there's been a steady progression of exploration of more complex traps, so with more electrodes and with the ability to move ions around. And you see here a wiring problem, if you like. This is a system, this is a chip trap where ions are trapped above the surface of the chip. So there'll be an ion above a surface. And you see there now multiple electronics being used to actually control the potentials of this trap, all inside a cryostat, actually, which is that sort of system. So there's been a steady progression of exploration into these sort of chip traps. I think they still don't work as well in many respects as the bigger structures, but we're learning how to do this. So one of the challenges that's relatively immature is the optical wiring of our ion trap system. So if you came to many labs today, you would see something like this. This is actually from the first lab that we built up at ETH Zurich. And what you see is macroscopic mirror mounts, and you see light that gets coupled into these systems in free space. Yeah. Now, as we think towards scaling, what we think about is systems such as this. What you see is all these little dots. That's meant to be individual ions, where you're able to have ions in lots of separate regions of a larger chip. And one of the challenges there, or one of the great advantages there actually, is that you should be able to put light into multiple regions of such a chip simultaneously. And so you can start to parallelize greatly the gates that you can perform on this chip. But actually, one of the challenges is persuading your graduate students to line up laser beams that go through multiple regions of a chip, because actually each set of laser beams has to be extremely well aligned into a particular region. And asking people to do that with more than one region is something that I think they're sensible to say this isn't a good way to progress. So what I'm going to tell you about today is instead trying recent results we had where we were doing this instead by directly taking optical fibers and coupling them into waveguides on a chip structure. So in a sense, what this is the optical wiring aspect of chips. You couple the light into the chip, and the chip delivers the light to the multiple regions where you want it to appear. So in reality, I've sort of drawn it terribly out of scale here. So the ions would be trapped somewhere over here, and here are the optical wires. These would be waveguides coming through to that ion region. Yeah, and in fact, that's a picture of our chip, right? It sits inside a 4K chamber. This part here is not to scale, and I'll show you more pictures later. So this, I should say, we're not the first group to explore this. So at MIT and Lincoln Labs, Rajiv Ram and John Ciavarini and co-workers did some experiments in 2016 where they did single qubit gates performed via light delivered by the chip. In fact, they've extended that now. So that was all done at a single wavelength, 670 nanometers. And that's now been extended now into the UV. So they can actually completely control their ions, deliver all the types of light that they want to the ions to do quantum control. But they face a challenge, and that's the challenge that we've been working on, if you like, that they have a very large loss in the power from trying to couple into the chip to the delivery to the ion. So that's really been a focus of the work that we've been trying to perform. And I was lucky, I should say, that Karen Mehta is really the person who brought this work to ETH for us and has built up a lot of the photonics infrastructure for us. So the chips start to look something like this. So on the top, you see usually gold trap electrodes. So there we're applying radio frequency and electric and static potentials. And these allow us to generate the suitable trapping potentials for our charges, which sit about 50 microns up above the chip. And then you'll see there's a whole stack of things that are below that. So these are done on silicon wafers. So you'll see there's a silicon substrate sitting down at the bottom. There's then generally silicon dioxide spacer, but here is a layer which is going to be our optical guiding layers. These are where we've got silicon nitride waveguides. And then in order to shield the ion actually, and also there's two aspects of this. One is that you don't want charges in the silicon perturbing an ion that's sitting up above the surface. But the other is that we put radio frequency fields onto these trap electrodes, and we don't want that also driving processes in the silicon. So there's a ground plane here which tries to separate out what's going on electrically from any of the other stuff happening in the chip. So what you might notice from this, if you've done any lithography or fabrication, is that there's multiple processes involved here, right? So there's you've got to be able to do lithography of silicon nitride, pattern it actually, and I'll tell you a bit more about that in a moment. And then there's more materials that are coming in as you build up this stack. So Karen then started to work with this commercial foundry in the Netherlands called Lionix. And somehow a nice aspect of that is that they really work on a wafer and produce you a large range of designs of any one of different types of chips that you can try. Yeah. So the other thing that Lionix had, which was very nice, is this ability to do this, they call it triplex technology, to do this multi-layer silicon nitride patterning. So why do you have silicon nitride and silicon dioxide? This is like an optical fiber in a certain sense. You have a material of a different refractive index to its cladding, and that allows you to confine your optical mode into that region with this different refractive index. So in our case, that's silicon nitride, and that's good for wavelengths down to about 400 nanometers. So we have, there's two layers of that in this Lionix fabrication. One where they do a thick layer of silicon nitride, and then the optical mode is very well confined, but it's actually much more confined than your typical optical fiber. So that creates the problem that it's hard to match the optical mode of an optical fiber to the optical mode of silicon nitride. And so what this company does is actually also make in a separate layer a very thin layer of silicon nitride. And then they have a transition region where they get very good transmission from this type of waveguide to this type of waveguide. So this creates a larger optical mode. We match that to the fiber. And then when we want to route light on the chip, then we have this more confined mode for the routing. So the final part of this story is that I showed you these sort of patterns in the silicon nitride. And let me show you a top view of those patterns. So here's a waveguide coming in, light comes in here. It then expands out because the waveguide expands out horizontally. And these patterns are actually a 300 nanometer grating, and it's a diffraction grating. So when the light comes into that, it actually is designed such that the light diffracts not just up, but also down, and it reflects from the silicon. And by designing these gratings properly, then Karen's able to make the beams focus to a point above the chip. And in our initial experiments, we chose a rather large focus that would jointly illuminate 2 ions. So here you actually see a picture in the plane of the ions that we take with a microscope. And here are the 2 ions, if you like. That's where they're positioned. Well, that's not 2 ions, right? That's 2 blue dots, but they're positioned within the laser beam, right? And this is what we've been using for early experiments. So that's the story of the light. So here you see the actual chip looking down on it. It's the same chip you saw in the very first slide. Here are the electrical wire bonds, if you like. The radio frequency is supplied via these wires here. And on the left-hand side, you're seeing the V-groove array and the fibers, which are being used to bring the light in. So in the middle of this chip, in this region here, if I just go to the next slide, then, sorry, that didn't respond. Good. Okay, I'm having trouble with response times in Zoom. Okay, so here what you see is actually 3 regions. And in the middle electrodes here, you'll see that there are cuts in the electrodes. And if you look carefully there, this is where the gratings are. And there's 2 types of grating. One here, which is for 729 nanometer light. That's what we use to resonantly drive our qubits. And the other used at 854 nanometers. And that's what we use for repumping typically. So in addition to this, I should say we're not fully optically integrated yet. There are additional beams that come across the surface of the chip to do Doppler cooling and readout in this setup. So the real thing that we pushed on in this experiment, if you like, was that this Line-X fabrication allowed us to match very well fiber modes. But it's still a problem to keep fiber modes of fibers very well aligned to the chip, especially as we wanted to cool this chip down from 300 to 7 or so Kelvin for operation. Yeah, that's really to get good vacuum and to have a flexible, fast turnaround for our setup. Yeah. So actually, Karen did a really great job of that. So he was able to get these fiber attached losses. So that's the light coming from the fiber into the chip down to the sort of 1.5 dB level. And it maintained that, and that's really a very high degree of alignment, all the way down from 300 to 7 Kelvin. And the nice thing about that is that here is now a single qubit gates, basically, on a trapped ion qubit, and we can get reasonably low pi times. In fact, we can go down to 2 or so microsecond pi times. So this, in a sense, is a repeat of the work that was already done at Lincoln Labs, except that our intensities are higher, so we can get much shorter pi times. And that's more important actually for realizing 2 qubit gates, because the 2 qubit gates require not just that your optical field has intensity, but you use a gradient of intensity, and that's sort of got a weaker coupling factor than for single qubit gates. So indeed, we now, the breakthrough, if you like, was that we were now able to do these multi-qubit gates using integrated photonics. And I should just say that one nice feature of that is that the light is reasonably well focused. 3 microns times 6 microns is a reasonably challenging waste to operate with if you're doing things in free space. But because the beam is coming from the chip, it's extremely stable in position relative to the ions. So in that sense, then you can, with relatively low powers of 1.5 milliwatts emitted from the coupler, we get gate times of 65 microseconds. And we were happy that the quality of these operations was actually very good. So we quantify that usually by doing an interference experiment with a maximally entangled state and looking primarily at the contrast of this interference experiment, as well as the population that we measure at the gate time. And there we see that we get fidelities of 99.3%. So these are not the best gates that anyone ever performed. People have now demonstrated gates near 99.9%. But when we look at our error budget, actually, I think we're happy in a certain sense, because many of these errors are things that where there is sort of an obvious problem that we know we could try and fix, but also we've not really done any error mitigation here. So there are many techniques that we know in quantum computing for doing gates with multiple pulses of light. And they, for instance, can be used to mitigate motional frequency drifts, laser frequency noise, which are some of our leading error sources. But I think in a certain sense, it's with such a new system, it's actually a sort of better quantification to look at more of a raw gate without trying to mitigate those things. So in that sense, I think it's very pleasing that we are quickly able to get to high fidelities, even without doing a lot of serious gate work. So let me just point beyond what we might do with single zones. So one of the big challenges in trapped ion work is actually to realize sort of regions where you can take ions through in multiple dimensions. And I'll come to that in a moment. But one of our devices that we came from the foundry already, if you like, does actually have one of these cross regions. And you can see in this device, there are many waveguides now going to many regions of the chip. And there are special regions of that chip. There's the junction, which was designed by Qi Zhang. But also we have a region here where there are actually 5 couplers, which all are intended to create a tight focus at individual ions. And so we've characterized the optical fields from that, and just you can see there 50 microns above the chip, there are really these nice 5 tight focuses, which hopefully once we're able to use these systems, we'll be trapping in that system and addressing individually these ions. Okay, so let me go a bit more in a theoretical direction, and we think about the challenges of scaling long-term trapped ion quantum computing. And as I told you, state of the art today is really working in these long linear chains in a big trap. But as we think to going to larger systems, we think we're going to have to break down those long chains into smaller units. That'll help us to get to higher fidelities. But there's and then we have to think about how to operate all of these zones in parallel. And the workhorse so far has always been the radio frequency trap. But radio frequency traps actually have some pretty big problems when you start to think about scaling, in my view. Yeah. So one is that the good conditions for trapping for quantum information tend to be where the radio frequency electric field is 0. Yeah. So there you don't have any driven motion. You just have that the ions can sit pretty static, yeah, but they're confined by this potential. But unfortunately, that can only really exist along a line, yeah. So what you see in this diagram with these junctions, actually going through these junctions creates highly non-ideal conditions for trying to trap and manipulate ions. And that means they're going to be very sensitive, I think, to noise and other problems. Another problem that's familiar to anyone who's worked with radio frequency traps is that to get to this point of the radio frequency null, typically you have to align your static potential exactly to that null, yeah? And that's often a daily or so task of experimenters, and as you go to higher levels of control, you have to do that better. And that's a challenge because the static potentials tend to drift due to lasers hitting electrodes or something like that. And finally, if you think about chip traps and you think about scaling them up to many zones, then the problem you have is that you drive now RF through many more wires, and these chip traps will heat up. And actually, that's already proving a challenge that has to be carefully thought about. So here's actually a heat map of a chip from Sandia National Labs, and they're looking at the IR emission, and you see that it's getting hot. Yeah. And this is still with a very small single zone or a few zones of trap in the very center of the chip. Yeah. So this power dissipation issue, I think, will become a much bigger problem as we go to larger systems. So the RF null 1D problem can be overcome if you think to yourself that instead of having all the ions in a single potential well, you rather have one ion in a potential well here and one ion in a potential well here. Yeah. Now the challenge is, can you get these separate potential wells close enough together to make them interact? Yeah. And this is useful because you can think about having potential wells in some 2D geometry and laying things out on a surface, and that gets you away from this 1D constraint. So the critical thing there is to get Coulomb coupling that's strong. And I'm just going to point out the form of the Coulomb coupling has. It's actually just like a dipole-dipole interaction in an RF trap. So in an RF trap, any oscillation happens along a given direction. And you can think about that as a charge distribution going up and down. And so it's actually, if you have another one sitting somewhere distant, it's like two of these oscillating charge distributions. And that's where you get something like a dipole-dipole coupling. And indeed, the scaling of the splitting between sort of normal modes, collective modes you get in that system goes as 1 over d cubed, which is what you get for dipole-dipole type coupling. And I just point out it goes as the 0-point motion squared as well. Okay, that's an interesting fact that hopefully will become relevant later. So the challenge that's been found with these individual ions in microtraps has been getting them close together. Okay, so usually in order to get them close together, you have to bring the ions close to the electrode surfaces, and those are noisy. So we get trouble with the motional modes. We also have to get laser beams in close to the surfaces, and that's also more challenging. The other thing, so if you can't get your ions close enough together, you basically can't split motional modes very much. Now, one thing I didn't emphasize enough earlier was that when I was thinking about the 2-qubit gate, I talked about driving this motion, and I exclusively said that's what was used for the gate. Now, off-resonantly, you will also drive collective motion, which is in phase of the two ions, and that actually weakens your gate in general, or it can strengthen it, but in general, you should think that the gate really works by isolating this type of motion in frequency space from this type of motion, yeah? So basically, the speed of gates is going to be limited if you can't get these ions close together, yeah? And that's a challenge already for these ions in radio frequency microtraps. So you might think, well, radio frequencies is not the only type of trap we know in ion trapping. In fact, the other type of trap is these penning traps, right? And in a penning trap, you have something where there's a potential which along, or I should go back, right? You've got a static potential, which is a quadrupole potential, and it's superposed on a large homogeneous magnetic field. And I didn't write the vector potential here, but I just want to give you an idea of this homogeneous magnetic field. So just to note that there's confinement from the static potential along the field, and then it's like sitting on a hill radially. The ions will try and fall down in the x and y directions, but their precession in the magnetic field will lead to them being confined. And penning traps are widely used, of course, in precision spectroscopy. You've probably heard many things about them in the last few weeks, but they're also used in quantum control. And these are beautiful experiments from John Bollinger's lab, where he's got sort of millimeter scale electrodes, right? You see that they're at 3 different potentials, creating this quadrupole potential in the center. And he has systems of 100 ions or so trapped in the center of this system here. So that's a beautiful many-body system, and he's used it for some very nice experiments on quantum simulations. So our idea is more thinking towards quantum computation and what we can do with these microtraps. And so our real thought is that instead of using microscopic RF potentials, let's replace that part of these microtraps where each ion is in an individual trap with the homogeneous magnetic field of a penning trap. And the advantage there really is that when you have static potentials, you create those by applying voltages to the trap. For a given voltage, you can always get a stronger static potential than you can a radio frequency pseudopotential. Yeah? And the reason for that is that, or at least for stable trapping you can. For stable trapping, then you have to work in a regime where the static curvature you produce is much stronger than the pseudopotential's curvature. Typically around 1 over 16 is that ratio. So what it means is that a penning trap array of this sort would require lower voltages than what you would require if you had radio frequency traps, primarily because the radio frequency trap has to generate confinement from this radio frequency field, and that's this pseudopotential. There are other big advantages when you're thinking about small traps. So there are only, there's static fields only here, so there's no power dissipation due to driving RF through these through any chip structure that you have. And there's a reduced sensitivity to stray fields because if this potential here is moved by some charging of an electrode somewhere, it moves you within a homogeneous field. And that's by a big contrast with the RF traps where this microscopic potential would move relative to this microscopic potential, and that causes a problem. Yeah, here should be less of a problem. So I just wanted to quickly mention that the challenges of thinking about that are sometimes in thinking about what the coupling should be. So in a penning trap, along the magnetic field, you expect standard oscillatory motion. But in the plane perpendicular to that, you get these sort of trajectories that you see here. And that's composed of two things. One, which is this modified cyclotron motion, which is sort of the precession, the natural precession you would get in a magnetic field, if you like. And then this drift term, which is actually a negative frequency oscillator, which is called this magnetron motion. So there are the sort of fast loops, if you like, and these slower drifts. In typical traps, and nearly every trap that you've seen operated, then these two frequencies are well separated. But there's no fundamental reason that that has to be the case. Yeah? Here it's the set of frequencies that you get. And here what I'm doing is I fixed the axial, the confining frequency of the quadrupole, and I'm essentially varying the magnetic field. And here goes the cyclotron motion to higher values. Here the magnetron motion comes down to lower values. And most traps are operated up here. But actually, we're quite interested in operating in this region here. And I'll show you why in a moment. So if you consider two traps near each other and ask about the couplings, you find that actually we were slightly surprised to find what the nature of the couplings were, in the sense that it's similar to the Hall trap. That's somewhat expected, that you get these sort of dipole-dipole couplings. But it's not so obvious when you've got these ions going around in these circles all the time that you should really get a dipole-dipole type coupling. Yeah. But nevertheless, we get such a coupling. And the interesting thing is that it's as though you didn't have them going around in circles in this direction, but it's dipoles as though they were going in the perpendicular direction up and down. Yeah. So actually the axial motion along the magnetic field, as well as the motion perpendicular to the magnetic field, both have the same type of dipole-dipole coupling. It's got a flipped sign for the magnetron motion because it's a negative frequency oscillator. And then you can look at what the strength of the coupling is. And you see that in this case, this is the axial motion that's got nothing to do with the magnetic field. It's just exactly the same expression you get for a Paul trap. But in these cyclotron and magnetron motions, it's actually different because the denominator here has the difference frequency between the cyclotron and the magnetron modes. And now you might see my interest in working down here because we can make this difference frequency small while keeping the mode frequencies high. Yeah? And indeed, then you might ask, what does the motion look like in this setup? So this motion that I drew here was a trajectory for the cyclotron being much larger in frequency than the magnetron. But if you think about that when these frequencies are quite close to each other, what you find is if you start here, you spiral in to the center and then you spiral both out to the side, right? So this is when the magnetron and cyclotron have just a little bit different frequencies. Yeah. So what's happening there? That's a superposition of motions from both the cyclotron and magnetron, right? And what's happening there is that as they get out of phase with each other, you spiral in, and as they get in phase again, you spiral out. Yeah. And the total time that it takes for the ions then to go up their potential hill and come back down the potential hill is related to the difference frequency of these two. And so you see that 0-point motion of an oscillator, somehow here in a very counterintuitive way, is due to the time scale over which you go up and down the potential hill. Only here you're doing that in this funny rotating frame system due to the magnetic field. So there are some nice advantages of that from the point of view of these microtraps. One is that if you have if you can tune into this regime, you can get large exchange couplings, yeah, large mode splittings, which allows potentially faster gates. Actually, when you come to couple lasers or magnetic field gradients to these, you get stronger couplings because the 0-point motion is an important factor that comes in there. And the disadvantage is that the heating of the ions is enhanced. Yeah, so heating of ions goes as 0-point motion squared. But a nice feature of that, and this is more a comment for the experts, is that you still sample noise at the raw frequencies of the modes. even though you don't sample at the difference frequency of these two. So somehow both of these effects appear that you get benefits from going to a difference frequency here, which is far below the actual frequencies of the modes, and you're somewhat protected by the fact that you sample noise still at the frequencies of the modes. So let me just show you how that might be used for computation on a fixed lattice. So the idea is that you have, say, a square lattice of 90 ions, and we select out two of the sites and move them to a slightly different frequency than the rest of the lattice. So at that point, the mode spectrum, and here there's a mode number, so I'm plotting all 300 or so, 280 modes, 270 modes of this system. Most of the modes are all tactily packed in these bands. This is frequency at the left-hand side, and these are the mode frequencies. But there are 6 modes corresponding to the motion primarily occupied by these two ions, which are very well separated from the two. And you'll see that those two are not very spaced at all, and that's because the ion separation is such that the axial modes with their small 0-point motion don't couple strongly to each other, but the cyclotron and magnetron modes do couple strongly to each other and split a lot, and actually also are split very far from the band. Yeah? So that's very nice because you can isolate these modes. They now have a large 0-point motion, so you can drive them easily with lasers, and you can do the calculations, and you see that you could, in terms of just considering motional effects, you can see that high fidelities could be achieved in short times. And this is a nice feature for laser people with a very small angle between, say, some Raman beams that you might be using. And why is that a nice feature? It's a nice feature because your wavelength is then long, and then you're relatively, or you can be less sensitive to temperature effects in your system. Okay, finally, let me just comment. Another sort of prospect for doing trapped ion quantum computing, and I've referred to it a few times, is not working with, say, long chains or just a fixed lattice, but moving these lattices around. And the big challenge of that, as I pointed out earlier, is these junctions. And in fact, the big challenge of those is that you, as you go through these junctions, you get sort of several microns of micromotion, of driven motion. And the penning trap avoids that because it just doesn't have micromotion. As long as you're adiabatic compared to these mode frequencies, then you should be able to move any of these trap sites in basically 3D, actually, by moving the static potentials. And I think that's a big advantage. I think this is quite a roadblock, as I see it. Even though we're trying to do these things today in our laboratory, we see theoretically even that it looks challenging to do that in a simple way. Yeah. So this seems to be an advantage of the penning trap. So let me summarize my talk then. First, I told you about some recent experimental work, which I think is very encouraging towards integrating optics for doing quantum control. In particular, we've been able to perform high fidelity multi-qubit gates. And then looking to the future, we've made this proposal, if you like, to use micro penning traps for scaling ion trap quantum computing sort of into 2D, if you like. That's all summarized in this paper. And I should just say, for more of you guys with a precision measurement background, there's some interesting things about normal modes of coupled systems of ions in penning traps there. And in particular, Shreyans came up with a very nice multi-ion invariance theorem, which generalizes this sort of Gabrielsi-Brown invariance theorem. So one of the nice things about being an experimentalist is now we get to set out on a quest to build these things. So indeed, the magnet arrived last week in a coronavirus lab. Yeah, so it's not sort of all being instantly built, but we're on the path to trying to investigate these new directions, and we have to hope that it works. All of the things I said were theoretical and thus complete speculation at this point. Yeah, so we have to do it. Yeah. So with that, I thank the team that I work with. In particular, the people in red I should highlight as working on the integrated optics work. And the people in green are the team pushing forward the penning trap, and in particular, Shreyans did a lot of the theoretical work. Sorry, I should have pointed out Matt Grau and Joseba Alonso, who's not named here because he's left, were also important in that theoretical work. So with that, I thank you for your attention and look forward to any questions that anyone has.